Okay, welcome to Psych 200 Research Methods. Today we're talking about the correlational research strategy. There isn't really a chapter for this in your book. This information is scattered, so it doesn't really fit with any of the chapters. So I'm just saying no chapter, but it is a lecture that we're gonna go over, and you do have to know it. Okay, so I guess I don't have an outline for this, but that's all right. So what is the goal of the correlational research strategy? What is it? What does this aim to do? Okay, well, it aims to establish that a relationship exists between variables and to describe the nature of the relationship. So the correlational research strategy, to put it simply, basically looks for correlations. It looks for relationships among variables. And you should already know something about this, okay? A lot of this, maybe most of it, will be review. We're going to talk about correlations and what they are and how to measure them. A lot of this should be reviews, just a little bit more detail, a little bit more in depth, okay? But yes, you want to determine that there are correlations. Like, is there a correlation, let's say, between sex and aggression, right? Does one sex, say males, exhibit more aggression than females? If that's true, then there is a correlation between biological sex and aggression, okay? Relationships can be described, okay? Keep in mind, relationships can be described. We can describe just like I have just done, right? But you can't really explain it. There's no real cause and effect there. So I can describe the relationship and say that males are more likely to exhibit aggression than females, that aggression, higher levels of aggression are associated with being male, for instance. But I can't really say that being male causes that aggression, okay? Because this is not an experiment, okay? We can't really talk about cause and effect. All we're doing is looking at correlations, okay? Correlations among variables, okay? And these variables can be from the survey that we talked about last week. So it was, so there was one part of the lecture last week that I didn't completely agree with, and that's the part that said that, that you don't really, you don't do anything with, like with surveys except try to describe what's there. Well, you can describe correlations, okay? So you can look for correlations. So if there was something mentioned that said that not interested in correlations, something like that, that's not really true. You can look for correlations. And by the way, if you're doing an honors project, you're required, okay, to have correlations or some type of t-test that we'll talk about later, okay, not today, all right? So the correlational research strategy is not an experiment, okay? There's no attempt to manipulate, right, independent variables, no, nothing like that, right? You don't try to control anything, right, or interfere with the variables. You just measure them, and like you would on a survey, and you try to determine if there's any relationships among those variables, like sex, let's say, and aggression, or relationship between, let's say, anxiety and, let's say, units that a student might be taking, okay? Something like that. It's easy to think of what some of those relationships might be. And just to differentiate here, there's a difference between different research strategies here. So experimental research, which we'll talk about later, right, is when you demonstrate a cause and effect relationship between two variables. You have an independent variable, a dependent variable. We'll talk about that later after the second exam. You don't need to know about it now because you're not going to be doing an experiment. Okay, that's just not allowed, okay? You can't really do that for an introductory class, not the way we have it set up here. And differential research is when you have two groups of scores and you focus on the difference between those two groups, okay? So differential research doesn't really determine cause and effect. So with differential research, which is more related to what we're talking about here, you can just measure, let's say, the aggression in males and females and see if one is higher than the other, or to see if there's a relationship, let's say, between being male and aggression, okay, or being male or female and aggressive behavior, right? You can just measure those things and determine a correlation. So you're not determining cause and effect. You're not doing an experiment. You're just looking at differences, okay? And if you can look at differences, you can also look at correlations, because if you're measuring things, you can always look at correlations. So just wanted to point that out. I could really cut this out. It's not really necessary that we mention this, but let's keep going. Now, how do you analyze the data for correlational studies? Well, you evaluate the relationships. You can evaluate the relationships among variables. You determine if there's a relationship, okay? So you look for correlations, okay? Now, it's easier when you have numerical scores, because remember, when you have numerical scores, that means that your variables, right, the measure of those are numbers, okay? So you have, let's say, a number for the variable aggression. So you have a certain number, right, for, you know, your 20 participants or something like that, or 50 participants. You have numbers, okay? And then let's say you have also another variable, let's say age, which is also a number. Then it's really easy to determine a correlation if you have numbers, because that's exactly what the way correlations are set up, okay? The math works with numbers, okay? So you have scores for each pair identified as X and Y. X could be aggression, Y could be age, okay? And then you can represent the data in a list, right? In which you're gonna have 2 scores for each individual. So for, you know, person A, let's say, or person 1, right? You have their aggression score, because you ask them about, let's say, how aggressive they are. And then you have their age. You ask them about their age. Person 2, you'll have their aggression score and their age. Okay, so you have numbers, okay, for both variables. And you can have a list of numbers, of course, for X, which is aggression, and, you know, you can have a list for Y, which is age, okay? And you can plot the scores on a scatter plot, okay? Remember that a scatter plot shows you, it illustrates a correlation, and, you know, and you can tell how things are related most of the time from looking at the scatter plot. So each individual score is shown as a single dot, okay? With a horizontal coordinate X and a vertical coordinate Y, okay? So you plot the point, okay? You plot the value for X, the value for, you look at the X and the Y, and then you know how to plot the point. And if you do that, you get scatter plots that look like this. Like right there, see person A for variable X, right? X is the horizontal line over here. For variable X, person A got a 1, okay? And for Y, they got a 3. So 3 on Y and 1 on X gives you a dot right there. You plot that. And then you plot all of those, right? All the other participants, and you can see the pattern there. And if you were to draw a line through that, right, you would draw a line going through those dots as best as you can, and that line would have a positive slope, telling you that it's basically, there is a positive correlation here between variable X and variable Y. Variable X might be, you know, aggression, and variable Y might be, you know, like I said, age or something like that, just to give you an example. This is easy to understand, okay? But you may not be used to the math or maybe how to plot these. Now, in my 101 class, I showed students how to do this. I showed them how to plot the points. We went through examples. You know, I asked them about, you know, how tall they are, and I asked them about how much they weigh, and they volunteered. I did this, right? I came up with the list there for their height, which that could be X, and the list for their weight, that could be Y. And then I plotted each of the points, and we found that there was a positive correlation. Okay, so let's talk about the consistency or strength of the relationship. Okay, this is also review. Okay, so remember, with a correlation, you know, or correlation coefficient is the term, right, for basically the variable that describes the correlation. The correlation coefficient is R. Okay, so the correlation or correlation coefficient measures and describes the relationship between 2 variables. If the sign is positive or negative, that indicates the relationship, I mean the direction of the relationship, okay? So a positive correlation, is it a negative correlation? The numerical value, the number, right, it could be from -1 to +1, indicates the strength or the consistency of the relationship, okay? The closer it is to -1, the stronger it is. The closer it is to +1, the stronger it is. The closer it is to 0, which is between -1 and +1, the weaker the relationship, the less consistent it is. And the type of correlation, whether it's Pearson or Spearman, right, indicates the form of the relationship. We'll talk about that briefly. That you probably haven't heard about, but you've heard of most of this stuff. Okay, so the direction. First, let's talk about the direction of the relationship. That's indicated by the sign, positive or negative. This should all be reviewed. If you have a positive relationship, that means the 2 variables change in the same direction. If one increases, or I should say if one is high, the other one is high, or if one is low, the other one is low. So if one increases, the other one increases. If one decreases, the other one decreases. I don't like the term there, increase or decrease, because that sounds like we're talking about cause and effect. It would be better if it said if one is high, the other one is high. If one is low, the other one is low. That doesn't indicate that there's anything affecting the other variable, that they're just related. But that, you know what I mean, a positive relationship. It means if one is high, the other one's high. If one is low, the other one is low. They move up and down in the same direction. Okay? Now with a negative relationship, we have the opposite. That means the two variables change in opposite directions. If one is high, the other one is low. Or if, let's say, one increases, the other one decreases. But like I said, I don't like increase and decrease because it sounds like we're talking about cause and effect, but we're not here. We're just talking about relationships. So I gave you an example of a positive relationship already, actually a couple relationship, let's say between, for example, height and weight. If height is high, right? If someone's really tall, they probably also weigh more. If someone is really short, they're probably weigh less. Okay, that's a positive relationship. But keep in mind that this works with several participants. Okay, you need not with one or just a couple. It works with if you have several participants. Okay, because you can have tall people who don't weigh very much. You can have someone that's 6 feet tall who weighs 120 pounds. Okay, and you can have someone who's 5 feet tall who weighs 200 pounds. Okay, so you can have the reverse, and that does exist. But when you measure the height and weight of a bunch of people, you'll see that on average, taller people usually weigh more and shorter people usually weigh less. There's a relationship. It's not perfect. If it was perfect, that means that every single person who is taller also weighs more, and every single person who is shorter also weighs less. And you have a perfect relationship, and you can predict one from the other very easily. Well, I'll talk about that later, but the relationship is not perfect, okay? There could be some people who kind of don't fit sort of the pattern here, and they would weaken the relationship. Now with a negative relationship, I'll give you an example of that. Let's say the older you are, usually the less healthy you are, for instance. Just to give you an example, not all old people are unhealthy, but usually when you're older, that's when your health starts to suffer. And you're usually healthier when you're younger. So the younger you are, right, the lower your age, the healthier you are. You're usually healthier when you're younger, okay? So that would be a negative relationship. Let's keep going because I'm saying too much here. The strength of a relationship, you can tell the strength of the relationship by how tightly clustered the points are around, let's say, a line, right? Remember, the strength also refers to the consistency. So right here, the scatter plot A over here on the upper left, that's R equals 0.90. Remember, as high as it can go is R equals 1, okay? So that relationship is close to being perfect, and you can see the points clustered around a line there with a positive slope. That's 0.9. If R was equal to 1, the line would be perfectly straight. Those dots would be perfectly in a line, okay? So the more tightly clustered the points are around a line, the stronger the relationship, okay? Here we have R equals negative 0.40. So now the points cluster around a line with a negative slope. You can see there, if you were to draw a line, it would, well, I can't really show you because, well, I wish I had a laser pointer here. That's probably a way to do this in Zoom, but I don't really know how. But anyway, that's a negative relationship. And you can see that negative 0.40, well, the points are a little bit more scattered, okay? But the relationship is negative, okay? So it's not as strong as 0.9 because it's closer to 0, okay? But the relationship is negative. It's you have a negative slope there, okay? And here we have R equals -1, C there on the lower left, okay? R equals -1. That is what we call a perfect negative relationship. The slope is negative. And if you look at R equals -0.4, the line should slope similarly, except the points are more scattered. But here you can see the points are clustered perfectly along that line, but it's negative, okay? that means, you know, that it's a perfect relationship. That is as strong as our relationship gets. R equals negative 0.1. R equals positive 0.1, by the way, is just as strong, okay? It's just as consistent, except that one is positive, one is negative. That won't be positive, this one is negative. And R equals 0, the points are, well, are kind of all spread out, okay? You can't really tell if it's negative or positive. That means there's no relationship. What that means is that if I know one thing, I know nothing about the other thing. If there's a zero relationship, let's say between age and health, let's say there's no relationship, that means if I know how old you are, I can't kind of guess at how healthy you are. I don't know anything about it. Those two things are not related. But in reality, health and age are related. Usually when you're older, and I mean much older, you're less healthy, okay? The form of the relationship has to do whether we're talking about a relationship where you have a straight line or one where you have a line that is not really straight, which I'll show you in a moment. So you guys are used to, when you guys talked about relationships or when you learned about it, you learned probably about linear relationships where the data points, in the scatter plot tend to cluster along a straight line. Those are the kind of relationships we just looked at. The points tend to cluster around a straight line, okay? Like example, a positive linear relationship. Each time the X variable increases by 1 point, let's say the Y variable increases as well by a predictable amount. By the way, if X increases by 1 point and Y increases by 1 point, and you have a whole bunch of, you test a bunch of people and you find the same thing for all of them, that would mean that the relationship R basically would be perfect. Okay, but usually variable X increases, let's say, by 1 point, and Y increases by a certain amount as well. But if it's not exactly the same, it wouldn't be a perfect relationship. But that's what I mean by positive. If X decreases by 1 point, then Y would decrease by a certain amount, okay? That's a positive linear relationship. It's just the kind of relationship you guys have been learning about, where the points cluster around a straight line, okay? Now, we measure that with what's called a Pearson correlation. A Pearson correlation describes and measures linear relationships when both variables are numerical, right? When we have both variables can be measured with a number, okay? Which is the easiest case, right? That's the easiest way to determine relationships. Both variables are measured with numbers, let's say like age, and the other one, let's say, is age, let's say, and aggression, and they're both measured with a number, okay? You would use a Pearson correlation. And I don't tell you so much about monotonic relationships, but I do show you an image. So with the Pearson with a linear correlation, that's A, right? You use the Pearson correlation for that. If you have a relationship that's curvilinear, that's called a monotonic relationship. And that is measured instead with Pearson. So they sound the same, actually. Pearson correlation describes linear relationships. Okay, no, actually, no. The other one is, they sound the same. I'm not really telling you the other one, but the other one is Spearman. Okay, let me make sure. Yeah, Pearson or Spearman. So the linear one is Pearson. You use a Pearson correlation when you're indicating which statistics you're going to use. And this one, in the monotonic, you use Spearman. One is Pearson, the other was Spearman. They're very similar, okay? It's almost like the same letters making up those names, so it's very easy to confuse the two. But linear is really what you guys have to know, okay? But you might be asked about Spearman, just like, what it's used for. It's used for when you have a non-linear relationship, a curvilinear one, okay? Now let's talk about how you evaluate relationships when you have, let's say one score numerical and the other one is not numerical, okay? So evaluating relationships for non-numerical scores and nominal scales, okay? So when you have one numerical score and the other one is non-numerical, so let's say that one is a score like age, right? It's a number, and the other one is not a number. Let's say the other one is sex, right? Here, let me give you this example instead. So one is the numerical score, let's say like aggression, and the other one is sex, let's say, right? Male or female. So one is a score, the other one is a category. How do you do a correlation with these? Okay, there's a way to do it. You use the non-numerical score, the one that's a category, to organize the scores into separate groups. Okay, and then the non-numerical value, and then you basically, the non-numerical value with two categories can be coded as 0 and 1. So to put that simply, what you do is basically, so the variable that's a category, let's say like male and female, what you do is you assign a 0 or a 1 to the categories. Okay, so let's say we assign males to be 1 and females to be 0. Okay, so we just turned sex into a number. We coded it differently. You have two simple groups, right? So females are 0 and males are 1. Now, which one you give a 0 to and which one you give a 1 doesn't always matter, okay? But if my other variable is aggression, let's say, if it's aggression, and I expect males to be aggression, then I should give males the higher number. I should give males the 1 and females the 0. Because then, when I do the correlation, I can find a positive correlation. And the positive correlation would tell me that if you're male, you're more likely to be aggressive, right? Or sex is associated with aggression behavior, meaning that males are more aggressive. Okay, so if I were to do it the other way, if I assign females with the 1 and males as the 0, then I would find a negative correlation between aggression and sex. And what would that mean? That would be a little bit harder to explain. So whoever you're expecting to have the higher level of aggression should get the higher number. Okay, but all basically you need to know here is that you have to recode the variables. Okay, so if you have a categorical variable where you have male, female, one gets a 0, one gets a 1, and then the other variable is already a number. Okay, so now you have both of them as numbers, and now you can do the Pearson correlation, but you have to do a form called the point biserial correlation. Okay, so that's just statistics. Okay. What about if both variables are non-numerical? What about if both variables, let's say, are categories? So you have, again, sex, male or female, right? And then you have another variable. Let's say, did they pass the test or did they fail the test? So, you know, succeed or fail. When you have both variables, non-numerical, when they're both categories, let's say, and let's say they're both, you know, yeah, they're both categories, then you have to organize it in a matrix like here, where one variable will form the rows, okay? Like male, the upper row is male, the bottom row is female. And the second variable will form the columns. Succeed is, you know, the first column and fail is the second column. And you organize it like that. You put it in a matrix, okay? And you do what's called a chi-square test. Chi-square test of independence. What you're looking for is you're trying to determine whether, let's say, success and failure is independent of being male or female, okay? So that's what a chi-square test does. Now keep in mind here, so you have, let's say, you had 20 males participate and 20 females, because if you look at males going across, there's 12 that succeeded and 8 that failed. Okay, that's a total of 20. You have 20 females as well. There's 17 that succeeded and 3 that failed, okay? So what you're looking for is basically, is there a different pattern of success and failure for males or females? You organize it in a matrix and then you can do the chi-square test, okay? I'm just telling you guys how this is done. I'm not really gonna show you guys how to do it today. I'm gonna show you guys how to do that when we talk about statistics. Okay, right now we're just talking about it. I'm not really gonna show you how to do a chi-square test because what we're gonna use is something called Excel. There's a Google version of it. I forget what it's called. But anyway, I don't know how to do the chi-square test on there, but I'll show you how to do other things. Okay, I'll show you how to do a correlation. I'll show you how to do a t-test, mean, standard deviation, some of the basics, but I don't know how to do the chi-square test using those programs. Okay, so I'm only gonna tell you about the chi-square test. I'm not gonna require you to calculate it. I'm only telling you about it. Guidelines for interpreting the strength of the correlations. So how do you know how strong your correlation is? Okay. So you do know already, I told you already, that the closer it is to +1 or -1, that means the correlation is strong, okay? That it's stronger the closer it is to +1 or the closer it is to -1. The closer it is to 0, the weaker it is, right? You should know that from Psych 101 already. But there's a little extra step that you have to do in order to determine how strong a correlation really is, okay? You have to determine what's called the coefficient of determination. And that is the square value of the correlation. So in other words, in order to know how strong a correlation is, you have to square it. And by the way, when you square the correlation, the sign basically no longer becomes important. So if you square, let's say R equals 0.10, you get R squared equals 0.01, okay, which stands for 1%. By the way, if you square R equals -0.10, you get exactly the same number. R squared equals 0.01. That means that R equals -0.01 and R equals, 0.01 are equally strong. The sign doesn't make a difference when determining the strength of the correlation, because when you square it, the sign becomes meaningless. If you square two negatives, you get a positive. If you square two positives, you still have a positive. So the sign doesn't matter when it comes to the strength. R equals -0.1 and R equals +0.1 are equally strong, and they both tell you they can both basically predict about 1% of the variation. That's what that means, right? R squared equals 0.01 is 1%. 0.01 is 1%. That means that if there's a relationship, let's say between age, let's say, and let's say health, to put it that way, right? And the correlation is R equals 0.10. That means that if I know let's say your age, I can predict your health with about 1% accuracy. That's what that means. I have a 1% chance of predicting how healthy you are. It's not a very strong correlation. R equals 0.10 or R equals -0.10. That's equally strong. You have about a 1% chance of knowing the second variable if you know the first. That's what that means. If you have a medium correlation, R equals 0.30, if you square it, that's R equals 0.09, that's 9%. So if you know one variable, you have a 9% chance of being able to guess the exact value of the other. Large correlations are 0.50 or higher, right? If you square 0.50, you get R squared equals 0.25, 25%. So if you know one variable, there's a 25% chance you can guess the other. You can predict the other one with 25% accuracy. That's what that means. That's a large correlation. Okay, so if I know, let's say your age, I can predict your health with about 25% accuracy. That doesn't sound like much, but that's a large correlation. Now, let's do it one that's even higher. Let's say if R equals 0.90, right? R equals 0.90. That means if I know one variable, then if I know the value of one variable, I can predict the other one with 81% accuracy, because 0.90 squared is 0.81, which stands for 81%. And that is a very high degree of certainty, right? If you predict one, you have an 81% chance of being able to predict the other. So you can see the higher the correlation, the greater chance you have of being able to predict the other variable, because it is really about prediction. This is really what this is about, okay? But in order to determine the percentage, right, the chances of predicting one, right, the probability, right, you have to square the correlation. That's what the coefficient of determination is. That's what it says, right? It measures the percentage of variability in one variable that can be determined or predicted by the relationship with the other variable. So if the relationship is 0.50, then I can predict the other variable with 25% accuracy. Another way of putting that is I can predict about 25% of the variability. That's what that means, right? That's the coefficient of determination. That might sound a little bit strange, right? Because you're not used to hearing about this, but it's really easy, okay? Square the correlation, and then that tells you the percentage, your chance, your probability, right? The chances that you can predict one variable if you know the other. That's what that means. Because this gets us into what we call prediction. If you want to predict one variable from another, right, you'll find out in a moment that that's called regression, okay, which is a fancier type of statistical analysis that's based on correlation. But yes, we often want to predict one variable from another. So if I know X, let's say, to what extent do I know Y? Can I predict Y? That's prediction. That is called regression, which some of you may have heard about, but you'll definitely hear about it when you go to graduate school, or maybe in a higher level class that you might take when you transfer. So you can predict one variable from another. So a correlational study demonstrating a relationship between two variables, right? You know, that can be used to predict one variable from another. So a correlational study demonstrating a relationship between two variables, right? You can use the knowledge about one variable to help you predict or explain the second variable. That's what that means, okay? So if you know, let's say, the correlation between the variables, you can predict one variable from another, okay? So these two variables, right? There's two variables. You need at least two variables in order to do a correlation. One of them is called the predictor variable. That's the first variable. And the other one's called the criterion variable. That's the second variable. That's the one you're trying to predict or you're trying to explain. So let's say I know your age, right? That's X, okay? That's my first variable. That's my predictor variable, let's say, right? And I want to be able to predict your second variable, right? Your health. That would be my criterion variable. That's the one I'm trying to explain. That's the one I'm trying to predict. Okay? And regression is simply that. Regression is the process of using one variable to predict another. And it's based on correlation. Okay, it's based on correlation. If two variables are correlated, that means you can use your knowledge of one to predict the other. It's actually, in principle, it's very simple. Okay, but of course it involves math to do this. Okay, it involves statistics. But conceptually, it's actually easy, okay? So regression is a fancy way, it's a fancy application of correlation, okay? But it's basically the same thing, okay, if you just think about it, okay? So regression is the statistical process of using one variable to predict another, okay? So the goal is to find, let's say, an equation that produces the most accurate prediction of Y, right, the criterion variable, for each value of X, the predictor variable. So X, let's say, is age, and Y is health. I know your age, I want to be able to predict your health, okay? I can use regression, right, to determine this. The predictor variable is relatively simple and well-defined. The predictor variable, the one you're trying to use, is easy, right? Age is easy. We can measure that very easy. We can just ask you, okay? We can check your birth certificate so we can see when you were born. And then, you know, see how many years it's been since you were born. Another example of predictor variable might be income. Relatively simple, well-defined, easy to measure income. You can just ask people, or you can check their pay stub. You can see how much money they make. It's easy, right? That's the predictor variable. The criterion variable is usually more complex and more unknown. Let's say like your intelligence or your health or your aggression or something like that. So the criterion is the one you're trying to predict. That's the one that's usually more complicated. So I can predict, let's say, I can try to predict, let's say, based on income, your intelligence. And that is, you know, that is let's say, a very bad way to think of intelligence, okay? But there are people who believe that, you know, your intelligence and your income are related. They believe that people who are more intelligent, basically, should, because of their intelligence, be able to eventually earn more money in the future. They should be able to get better, let's say, scores on their tests, get better grades, get higher degrees, and therefore get a better job that's going to make them more money. There's a relationship between income and intelligence, okay? Now, keep in mind, we're talking about correlation here. That doesn't mean that, you know, intelligence causes income or that income causes intelligence, okay? Because if you believe that, that would mean that the richer people are more intelligent than the poor people. And that's probably not true. What it does mean is that people who have more money have more advantages that allow them to basically do better and score better on those intelligence tests. And of course, also get better jobs. Okay, but there is a relationship there. We can try to predict, let's say, your intelligence from your income, or that sounds like a kind of, believe it or not, a very, you know, a racist kind of example, believe it or not, or one that's kind of biased, or one that's seems like, you know, this issue where people argue about a lot, you know, where they talk about class warfare, right? Rich versus poor, that kind of stuff, right? It gets into political stuff. But I could have said, instead of income, I could have said, let's say your age, and then I could have said like your health, right? That would have been an example that's less controversial. This is, you know, one that really gets people upset when they think about this, for good reason. But remember, we're not talking about cause and effect here. We're just talking about correlation. There are many reasons why those with higher income would seem to be more intelligent, or would seem to score higher on those intelligence tests. That doesn't mean that they actually are more intelligent. It just means they have advantages. Okay, it's a correlation. But anyway, I probably said too much there, and I probably confused you, but you can predict one variable from another, okay? Now, here's something a little bit more useful and more complicated so you can determine the relationship. And I'm starting to remember now why I use that example of income and intelligence, okay? Because it's actually not as simple as it sounds. Okay, you can try to determine relationships with more than two variables, okay? So instead of trying to predict, let's say, one thing from one variable, right? You can try to predict one thing, let's say your intelligence, from multiple variables. And when you do that, that's called multiple regression. It's a statistical procedure for studying multivariate relationships. You're trying to determine the relationship among multiple variables. Because I'll tell you this, and this is actually the truth. This over here seems like a very kind of controversial example that you can predict intelligence from income, right? That's regression, okay? However, in real life, it's more complicated to try to predict. It's more complicated than that. Intelligence is something you can predict, not just from income, but from other things related to income, okay? Like education. And if you have a better income, it usually means your kids get to go to a better school. You go to a better school, right? And also privilege. Race is also correlated with income. So are things like health and less exposure to pollutants and toxins, because richer people also tend to live in areas where there's cleaner air, and they don't live next to the power plant that's emitting all these toxins that's bad for the brain and bad for the blood and things like that. So there's actually multiple things that can predict intelligence, not just income, but a whole bunch of other things that usually have to do with privilege, okay? So that's why we need to think about multiple regression. It's not one thing that predicts intelligence, it's many things, okay? Here's another example for you guys. Collins and Ellickson in 2004 applied an integrated model to predict smoking behavior for adolescents in the 10th grade. We can try to predict smoking. Who is more likely to smoke? What is it? What is that predicts that? You could do a simple regression, right? Simple equation, right? Where you try to say, okay, well, maybe, let's say, you know, like if their friends smoke, they're more likely to smoke. Okay, that would be regression, right? Univariate regression, where you're trying to predict one variable from another. You're trying to predict smoking behavior, let's say from their friends smoking, whether their friends smoke or not, right? If you're going to do multiple regression, then that means you're going to look at multiple variables. It's not just one thing that affects whether you're going to smoke or not as a teenager. You know what's going to affect whether you're going to smoke or not as a teenager? It's not just going to be whether your friends smoke, but also whether your parents smoke. It's also going to be advertising. It's also going to be, to some extent, you know, disposable income, having extra money to spend on cigarettes, because they are expensive and the expense adds up really quickly. People who are highly addicted to smoking will spend hundreds of dollars. Okay, hundreds, maybe $500, $700, or even $1,000 on smoking cigarettes per month. Okay, it gets expensive really fast, right? Especially if you're smoking several packs a day. Okay, so there are actually many things that will predict smoking. Okay, not just whether your friends smoke, but also whether your parents smoke, whether you have disposable income. Here's another thing that affects smoking. Also, your sex will affect smoking. Whether you're male or female. Your age, well, I guess if this is just among 10th graders, then age wouldn't matter. It's just for 10th graders, let's say. But there's lots of things that predict smoking. Just as there are lots of things that predict intelligence. It's not just income. Yes, it is true that rich people do happen to score better on those intelligence tests, but that's because they have a whole bunch of privileges. There's a whole bunch of other variables, okay? So multiple regression can be used to examine the relation between two specific variables, right? You can control the influence of other potentially confounding variables. There are other variables that could also affect the relationship that you can control. You can hold those constant, okay? I'm not gonna get into that too much, but multiple regression allows you to do that. When you look at multiple variables, you can check to see how they are related, and you can hold some variables constant, like let's say, you can hold age constant, okay? So you can make it so that you only do your study, let's say among those that are in the 10th grade. And I guess they would be, how old would they be? They're all maybe 16. So you do it just among 16-year-olds. So age doesn't vary. Age is not a variable. But you look at all the other variables while making sure that age is constant. You control the effect of age. That might sound a little bit beyond what you understand right now, but that's what that means. Okay, now, by the way, I'm not going to require you to do multiple regression. I know how to do this, and it would be really nice for those of you who are really advanced and want to do an honors project to do multiple regression. And I would love to do that with you guys and really take you beyond just what you would do as in an introductory class. The problem is that we don't have the software, okay? We would need something like SPSS, and we would need all of you to have access to that. We would need a lab with that program. I have asked for that, by the way, because I know that's the best way to teach this class is to have software like that. So I can really take all of you beyond just, the basics, and especially those of you who are doing an honors project who really want to challenge yourselves, but we can't. So as far as I'll take you is basically correlation and looking for differences, doing t-tests and things like that, because I'm not sure we can do multiple regression with something like Excel, let's say, or in Google, whatever it's called, Google, I think it's the Google version of that, okay? I want you to know what it is, okay? That's multiple regression. Reporting results from multiple regression, remember that the predictor variables only predict, okay? Those are the ones you're using to predict the other thing, and that you're only describing the relationships. You're not explaining the relationship, okay? People get into trouble when they try to say that there's cause and effect. When people say, for instance, that income causes intelligence or that intelligence causes income, that seems like a very biased thing to say. That almost seems like a racist thing to say or something that really awful to say, but you're basically saying that basically richer people are basically superior, that they're more intelligent. That's not what regression tells you or what correlation tells you. It just tells you that the two things are related, they're associated. It doesn't mean they cause each other. Remember, there are many variables in the real world that are actually acting upon intelligence. There are many things that determine intelligence. Some of it, yes, is biology, okay? But there's also other things like education and privilege. And yes, income matters, and so does health. So do many things, okay? And it's not something that's easy to explain, intelligence. There are multiple things that predict it. But to say that it's only one thing, like for instance, it's only income, or that it's only biology, those are things you can get into trouble for saying things like that, okay? Because those are very awful things to say. To say that, for instance, one group is superior to another. It's not that simple. It's usually the case that the group that's scoring better, that's doing better, actually has advantages that the other group does not. There are many variables. It's not a simple, simple relationship between two variables, and it certainly isn't necessarily cause and effect. Okay, I don't know how much I can tell you guys about that, but I've said it many times already. Reliability and validity, yes, when you do correlations, you can determine the reliability of something, the validity of something. And we actually already talked about this. So I'm not going to say much more about it. But reliability evaluates the consistency or stability of measurements. We talked about that. If a measure is reliable, that means if you give the measure once to a group of people, and then you give them the same measure, let's say a second time, let's say a week later, their score should be similar. The measure is reliable. Now, validity evaluates the extent to which the measurement procedure actually measures what it claims to be measuring. So if you have an intelligence test, right, and you claim it measures intelligence, right? If it's valid, that means it really does measure intelligence. Or if it's not valid, that means it could be measuring something else, not really intelligence. Maybe it's just measuring privilege, okay? Or cultural knowledge or things like that. And we talked about things like that. That's why when we talk about intelligence, it's something very controversial to talk about. And it's especially controversial to be making claims of cause and effect when it comes to intelligence. What is causing it? Right? If you believe it's only biology, then that means that you believe that basically certain people are just biologically superior to others. But intelligence is actually multifactorial. There's actually many things that determine intelligence. Okay? So when you're talking about the validity of a certain measurement, you have to think about that. Intelligence is complicated. It's complicated to measure, and to even talk about things that have to do with cause and effect, well, that's very hard. The only thing that tells you about cause and effect, by the way, is an experiment. And well, experiments that have to do with intelligence, you know, I don't know how you really do that. You probably can, but they'd have a lot of problems, okay? But yeah, you can definitely try to measure intelligence. Whether it's valid is another issue, and it actually relates to many different things, okay? Both reliability and validity are defined by relationships that are established using the correlational research design. Both reliability and validity are determined by correlation. We talked about that already. We had a whole chapter where we talked about variables and this kind of thing. Strengths and weaknesses of the correlational research strategy. So the strengths, okay, so you can describe the relationships between variables, okay? So yeah, you can do that, and relationships can tell you things, right? It's also non-intrusive, right? You can look at natural behaviors. You can determine correlations among things you observe, let's say, or things that you measure, right? Okay. You don't do experiments. That would be very obtrusive, by the way, the opposite of non-obtrusive, right? And that wouldn't be natural in an experiment. And you have high external validity because you're measuring real behavior or observing real behavior, and you can then determine correlations, right? That means you can really generalize your findings. That's what external validity means. But as you can imagine, the correlational research strategy has a lot of weaknesses, important weaknesses. You cannot assess causality, okay? You can't determine cause and effect, and that's something that people often forget, especially those that are not trained in methods, that are not trained on how to do research, especially those in the media or politicians or people out there, okay? They read about one study that talks about a correlation, and then they want to go ahead and make claims how this thing causes that. How basically, you know, how basically people who are rich are basically more intelligent than people who are poor. That is not true, okay? It is not cause and effect. It is a correlation, and correlations are more complicated than they seem. It's usually multiple variables correlated with multiple other variables, okay? We talked about the simple case of one-on-one, right? Two variables, right? That's for you guys to understand. But in the real world, things are complicated. There are many relationships acting all at once. It's not, you can't simply say that it's just this and that thing. And it's just wrong to say that it's cause and effect. You also have the third variable problem, the directionality problem, and low internal validity. We're going to talk about the third variable problem, directionality problem again. I believe we mentioned that already, so I'll go through it again, but more briefly because it has to do with correlation. Low internal validity, that basically means there's no cause and effect there. Internal validity has to do with that specifically, with cause and effect. And because it's just the correlation, it's not an experiment, right? It's the correlational research strategy. It is just, you're just looking at relationships. You're not really determining cause and effect. You don't have an independent variable, okay, that you're manipulating to then determine what the effect is on the dependent variable. That would be an experiment. What you do have is variables that you're measuring and determining differences between them, determining correlations, and that's not cause and effect. So low internal validity. So let's define some of these other weaknesses. The third variable problem is basically what that is that because two variables are related, that doesn't mean that there's a direct relationship between two variables. So maybe intelligence is related, let's say, to income. There's a relationship there. But there's probably a third variable that affects the relationship between those two things. There's a third unidentified variable, probably something we can call privilege, right? That is responsible for producing the correlation that you see. So there's a correlation, let's say, between income and intelligence. But there's probably a third thing called privilege, because those that have more income are also more privileged. And therefore, the intelligence test would be easier for them. They get better education, they have, better nutrition, better health, better circumstances. Everything's better when you're rich. Not everything, by the way, a lot of things, okay, but not everything. Some things are worse when you're rich, but most things are better, okay? But I won't get into that, into how things can be, worse, okay? But remember, there is a song that says, more money, more problems, okay? Or there's some lyrics, that basically say that. And for the most part, that's, to tell you a little bit more, that does seem to be the case. The more money you have, the more things you own, the more people work for you, and the more problems, okay? There's just a lot of things to take care of. If you want to be rich and not have a lot of problems, keep your life simple, okay? But usually rich people own a hell of a lot of things. They have big, expensive houses. They have people who work for them and clean their houses and cook for them and do all this stuff. And more people usually means more problems, more things. That's more things to maintain, more things to pay for, more bills, more problems, okay? But rich people usually have people who they hire to solve those problems for them, okay? But there are more problems when you are more wealthy. But you can really separate yourself from those problems by having other people solve those problems for you. But if you hire people who are crooked, by the way, who are not honest, they will steal your money, okay? That's the problem as well, okay? If you want to make sure you track your money yourself, right? Do everything yourself, right? Well, then you have to deal with all the problems yourself. In order to do that, you have to be intelligent too, by the way, and highly educated. It's usually not the case that one person can handle everything. There's also the directionality problem. A correlational study does not establish a cause and effect, a relationship of cause and effect. The relationality problem basically has to do with what's affecting what. A correlation doesn't tell you about cause and effect. So there's a problem with directionality. Now, here's some visuals for you guys to explain this stuff a little bit further. The third variable problem. Here's the thing. There is, believe it or not, there is a relationship between variable A and variable B. Ice cream consumption is related to crime rate. There's a positive correlation there. The more people consume ice cream, the higher the crime rate. That seems like a kind of crazy correlation. Why would those two things be related? But there is a positive relationship between them. And the reason there's a positive relationship between them is because they're both related to variable X. They're both related to temperature. When temperature goes up, guess what? Ice cream consumption goes up. More people buy ice cream. And also crime rate goes up. When temperature goes up, more people go outside and they do things outside. And when people go outside and they do things outside, they also beat each other up and stab each other and kill each other and hurt each other. When people encounter each other, they cause problems for each other. So when temperature goes up, crime rate goes up, so does ice cream consumption. So it looks like ice cream consumption and crime rate are directly related, but they're not. They are both related to variable X. That is the directionality problem. And I just told you about the bidirectionality problem as well, without intending to. And this is the same thing with intelligence. It seems that intelligence and income, let's say variable A and B, would be related. Let's say variable A is intelligence and variable B is income. They're related positively, right? Those that have more income score higher in those intelligence tests. Does that mean that those that have more income are just more intelligent? No, not necessarily. Both of those things are related to privilege and better education and better health and better nutrition and all sorts of better things. And if you take a child psychology class, developmental psychology class, you would learn about how all those things affect brain development. proper nutrition, proper health, less exposure to toxins, right? Better education, all those things matter, okay, when it comes to development of the brain and therefore intelligence. That's the third variable problem. There's the directionality problem is like this, okay? When you have two variables and they're related, it doesn't mean they necessarily cause each other, okay? It doesn't mean that one necessarily influences the other. The source of influence could be in either direction. So for instance, here is an example here for you guys. The sexual content of television programs that individuals choose to watch and sexual behavior of individuals is related. What that means is that when people watch television programs that have a lot of sex in them, they also tend to have higher incidence of sexual behavior. Other studies have shown like this kind of thing, that basically those that watch more sexuality on TV also start having sex earlier. Does that mean that watching sex on TV causes people to have sex earlier, or watching sex on TV causes people to have, you know, more sex or engage in more sexual behavior? Not necessarily. Remember, there is no cause and effect here. It is a correlation. It could be that the sexual behavior of individuals influences them to watch more sexual content on TV. And that would be the arrow going to the left, okay? So there are people who just by their very nature are more sexual than others. They like sex more than others, or they're more drawn to it. Therefore, they like to watch it more on TV, okay? It might also be the case that, you know, that watching a lot of sex on TV arouses you and causes you to engage in more sexual behavior. But the point is that the source of influence could go either way, right? Which way does it go? That's the bidirectionality problem. Well, the directionality problem. Bi means it could go both ways, but it's called the directionality problem. It could also be, by the way, that there's a third variable that's affecting both of them, like this, right? And that the two things maybe aren't directly related, but they're related to another thing. But that's the directionality problem. And we mentioned things like this before, I believe. It sounds familiar. By the way, that's the last slide. So I will stop recording.